Okay, so next topic is from BMW and Axia Technologies. Sadly, only BMW is able to be here today. So we are talking about TCP and Automotive Ethernet, how to resolve the everlasting struggle, part 2. Okay, so our speaker today, we have Karl Budweiser from BMW. He, since 2016, he worked for BMW as Automotive Ethernet and TSN architects. He focused on both EE architecture and system engineering. He helped and trained experts on TSN, TCP/IP, and some IP. And yes, from 2018 to 2021, he was chair of the Open Alliance Committee dedicated to switches semiconductors. He's also active in the TOSAR consortium and time validation and AVB. Okay, so Karl, your stage is yours.
Let me see how this works. Oh, this works perfectly. Okay. So, hello everyone. This is me. Actually, this is part 2 of me talking about TCP. Don't be afraid. You don't have to listen to part 1 to follow part 2. So it's not something like a series, an episode, something like running on Amazon or Netflix. But I would like to recap what we did where it makes sense with part 1. Last time, Iago from Technical Engineer and we investigated off-the-shelf TCP stacks used in embedded systems and showed how to tweak them to achieve both reliability and performance. These settings that we suggested, they are still heavily in use within BMW. We also teased back then in part 1 that the congestion control algorithms that are in use in automotive systems are designed agnostic of automotive networking constraints. So now, together with Axia Technologies, we designed congestion control algorithms with automotive networks in mind. And today I would like to show you that solution, that algorithm, and discuss pros and cons of the algorithm with you, because doing that is not that simple. So there is a reason that we didn't do that in part 1. To begin with, I'll recap TCP, as well as the main optimization measures that we discussed in part 1, and highlight the unresolved problem that our algorithm tries to solve. Then we will learn how the sending TCP can basically detect a gap in the byte stream before we're looking at the proposed algorithm and how this algorithm makes use of the knowledge on the existence of such a gap in the byte stream. Next, I'll represent example scenarios that help to understand the operating principle of the algorithm graphically. And next, we will shed some light on measurement results of a prototype implementation and see basically what are the limits of that solution based on different networking conditions, right? That solution has a certain operating range where it works good and a range where you might want to do something different. And last, the most important aspects are summarized and recapped, and I give you an outlook and something none of us should ever forget. Yeah. TCP, as you know, is a sliding window protocol that keeps book of all the transmissions by tracking basically the number of acknowledgements, the number of packets for which acknowledgements are missing or outstanding, the window of packets which is allowed to be transmitted, so that's the so-called sending or sliding window that is constrained or limited, bound by both receive window as well as congestion window. This is not shown here. As well as the number of packets that are not yet available because they are outside the sending window, so to say. TCP allows for parallel transmissions of all segments within that sliding window, and it is thereby trying to maximize the achievable throughput. Now, when doing that, it can go into the risk that it's overrunning the network. And to prevent that, there are certain mechanisms in place like flow control and congestion control that allow for dynamically reducing the size of the sending window so to not overrun the network. The retransmission policy basically explains when retransmissions are due. And typically, as long as the packets are coming in order, there are no acknowledgements. You will only see a TCP acknowledgement typically when an out-of-order segment is either coming in or a segment is coming in that is filling the gap. And this is very important for us because on that scheme, on that principle, our detection algorithm will be based on. The TCP itself has a couple of optimization measures. One of them is called the fast retransmit. And that means if you get just a couple of duplicate acknowledgements saying, hey, there is a problem, there is the gap in the stream, you can speed up retransmission of that very segment to try to fill the supposedly existing gap. If you haven't fast retransmit in place, your retransmission would be bound to the RTO timeout, right? But for us, the most important thing is a duplicate acknowledgement or a very quick acknowledgement is against the acknowledgement policy, and therefore it's a strong hint towards a packet gap. Yeah? So if you get debug, there is most likely a gap in your stream at the receiving side. In part 1, we discussed several optimization measures, and we showed thereby that tuning the RTO as well as enabling fast retransmit or traffic shaping lead to the best performance improvement. So that's what you need to know from part 1. If you want to make your TCP responsive, stable, you can stick with that. It's pretty independent and a sophisticated approach. In the figure on the right-hand side, you can revisit the issue encounter with many embedded stacks, and you also see why reduction of the RTO leads, leads to that kind of improvement. Basically, when reordering is supported, the lost packet, it's just replaced on the fly, thereby filling the gap, because the receiving TCP is able to store all the out-of-order segments, right? And you're just giving the receiver the missing piece, and it will just evolve, move forward the sliding window, actually receive window, and or the buffer state at the receiver, and thereby not losing too much bandwidth or performance at all. However, if it is not supported, so if out-of-order segments are dropped, because the receiver are not supporting the kind of reordering, any packet loss will result in a loss chain, because once you lose a packet, every packet after that packet is out of order. It's not the next one, it's the one after the next. So these kind of transceivers try or tend to delete those segments, and now you have to wait for the retransmission to provide the next segment in order. And that is bound to either a fast retransmit or an RTO timeout. And therefore, if you reduce the RTO timeout, you get your missing segments faster. But your network is still in that kind of loss chain state from which it can hardly recover. We will see how the recovery works, basically, how to come out of that. But you will tend to fall in again and again and again. Yeah? Before talking about the algorithm, I would like to share our assumptions with you, because that is very important. Without that assumptions, the algorithm wouldn't work, right? It's just a limited operating range with certain assumption, as always. Our first assumption is that the network per se does not cause any kind of reordering. So it maintains the order of packets. Yeah, it just loses packets, it doesn't reorder them. So most likely no rings, no alternative path through the network, all that is not covered here. We also assume that all the powerful issues, they're basically supporting reordering. Only the resource constraint issues, AutoSOXU for example, might not support the reordering, but they don't have that many TCP use cases. Yeah? So there are not many TCP use cases for that kind of issues. What's more, whenever there is a TCP use case for a resource constraint issue, it is either the resource constraint issue is receiving data via TCP, so it's being flashed, for example, or it's providing data via TCP to another powerful issue. Yeah? So this is typically not a problem. So what we need to take care of is shown here. Oh, sorry. Let's go back. Shown here. we have a powerful ECU, for example, that tries to reach out via these TCP to both resource-constrained and powerful ECUs. We may therefore wonder if or why the powerful ECUs couldn't just identify resource-constrained ECUs that do not support out-of-order queuing and adopt or adapt their retransmission scheme adaptively to overcome that shortcoming, right? Just changing how the packets are provided to those ECU. So that's basically already the basic idea. So to answer the question even better, let's look at the sending window of the sender. That's shown here. And the buffer situation, or the possible buffer situations at the receiver, once we get either a quick acknowledgement or a duplicate acknowledgement, in case that we have sent 3 segments. It's pretty much the simplest way. 3 segments have been transmitted, and now we got either a duplicate acknowledgement, meaning these 2 have been received successfully, but there is a gap. Yeah? The debug will therefore be triggered. Here, segment number 2 is received, and it says, hey, I'm lacking segment number 1. And this happens again, therefore a duplicate acknowledgement. Here it's a pretty quick acknowledgement. There is a gap, and you know the acknowledgement policy. If there is a gap, there is the TCP, the receiving one, will trigger a pretty quick acknowledgement. So these are, so to say, the basic situation that we can end up at the receiving side. So if we can figure out here that there must be a gap, we could basically just test if with any kind of retransmission we were able to successfully close a gap. Yeah? So we will go into that in more detail. I will show that how the algorithm is working in an example. But for now, I would like to show you the state machine of the algorithm, because it's actually not that complicated. We start off in the out-of-order mode here. In this mode, we are plain TCP, just retransmitting the last unacknowledged segment. Yeah? And now, if we are detecting a duplicate acknowledgement, we are checkpointing the sending window, meaning all these packets that are currently in transmission. We take a snapshot of that, and we move to the out-of-order monitoring state. So now we are testing if within that window, if there is a gap indeed, right? So if there was any retransmission in that, what we call flight window, or segments in transmission, call it what you want. If any of that retransmissions could be used to fill a gap, meaning, was there an acknowledgement that was acknowledging more than just the retransmitted segment? Yeah? That would be a so-called cumulative acknowledgement, and that means one of the retransmissions was able to close a gap. If this was successful, then the out-of-order queuing is supported, right? Therefore, we can go, if this turns out true, we can go back in the out-of-order mode. So normal TCP neighbor, normal TCP, or normal remote TCP, so to say, the receiver is all right. However, if the receiver is not able to support out-of-order queuing, or in other words, reordering, we have to go into the non-out-of-order mode. And this is where the magic happens. Upon entering the out-of-order mode, we collapse the sending window by setting the current segment that would have been sent and the segment, or that would be retransmitted, and the segment that we are currently at with sending out in line, we just identify these 2 with each other. So we collapse the window, and all the segments that have already been transmitted are due for transmission once again. So every retransmission is now a bulk or a go-back-N retransmission. Yeah? TCP actually sliding window that is retransmitting only the lost segment, but if the gaps cannot be closed, we need to wrap up, we need to provide the segments again in order. And this is what happens in this non-out-of-order mode. So our algorithm can break the retransmission chains by performing a go-back-N retransmission instead of that kind of selective retransmissions of the last unacknowledged packets, by detecting that the remote TCP is not properly supporting the out-of-order queuing. Now we go into a little more graphically. I guide you through how this works in detail. And for that, we assume that the sending TCP was receiving a quick acknowledgement. So you know the buffer situation could be like that. We either have 2 packets successfully received, 1 packet, meaning the next one after the one that needs to be retransmitted, or the one after. So 2 or 1 out of 3 are successfully received, depending on, this is the possible situation, so to say. In case 1 and 2, after retransmitting packet number 1, we get immediately a cumulative acknowledgement. So we are retransmitting this one which is missing here, and the gap can be filled, and we get an acknowledgement for segment number 4, which is due, which is the next expected one. Yeah, this is basically how the acknowledgements works. They're pointing to the next expected one. You could also think that packet number 3 is acknowledged, so to say. It doesn't make a difference. For the second case, it's almost the same. We get a cumulative acknowledgement saying after retransmission of packet number 1, we now expect packet number 3. Yeah? 2 was successfully stored, meaning this host supports out-of-order queuing. For the last case, we are not yet really sure. We retransmitted packet number 1, but we didn't get any acknowledgement, any cumulative acknowledgement. Therefore, we continue with the retransmission. And after replacing or retransmitting segment number 2, we also do get a cumulative acknowledgement, so everything is fine. This stack does indeed support out-of-order queuing, so we can stay in the out-of-order mode. Situation changes slightly if the remote TCP doesn't support out-of-order queuing. So again, we get an indication that there could be a gap here, and we therefore do a retransmission of segment number 1. But we don't get a cumulative acknowledgement in none of the cases. We just get a regular acknowledgement. So we need to try harder. It could be still case 3 with just the other, from the previous example. So we are also replacing or resending segment number 2 and hope for a cumulative acknowledgement, because the in-flight window was spanning from segment number 1 to 3. Yeah? So once we replace the second one, that's the last trial, if this one was successful, we would get, if out-of-order queuing was supported, a cumulative acknowledgement. But this doesn't happen, so we know for sure, again, that out-of-order queuing is in this case not supported. Yeah? This slide shows how the retransmissions are performed once we know that the out-of-order queuing is not supported. Instead of issuing the last unacknowledged packet, the algorithm works a little bit different. It is basically setting back this window and basically collapsing it. And is therefore sending all the packets that have already been sent once again, now in the right order, so provided that there was no other loss. If there was another loss, you remember the state machine, what happens? You would just do another bulk retransmission from actually that breakpoint, or from that base segment. So the solution is, so to say, to really carry out that go back N retransmission. In doing so, we will eventually get a cumulative acknowledgement, and we can basically speed up. And how fast we can speed up, you can see basically in our measurements, what's happening there. What is the gain? How does it perform? Yeah? The algorithm presented in the previous chapter is actually just augmenting the TCP, the congestion control, the native congestion control on the host, because it is not really changing when or how segments are transmitted. Yeah? There is still the congestion window. We still limit the burst size. What we change is basically just which segments are due for retransmission. And as the algorithm is just active when out-of-order queuing is not supported, it's not a surprise that the performance here when out-of-order queuing is supported is the same, regardless if you're using the algorithm or not. However, in case out-of-order queuing is not supported on the remote TCP, there is actually a gain visible. It's somewhat like 5 times higher in that case, the throughput, as if there was no out-of-order queuing and no algorithm in place. So a clear improvement there. Yeah, you get 5 times the data rate. That's good, pretty good. Again, we can recover, heal the system, so to say. However, there is a slight problem with that approach that you might want to fine-tune, and this problem, you can see that basically by looking at a simpler example. And that simpler example, for that we consider a file transfer with, again, the very same loss rate of losing every 200 segment. When out of order is supported, neither the transfer time nor the RTT is impaired, irrespective whether the algorithm is in use or not. This is here. So the time to transfer that file is almost the same, irrespective. Out of order queuing saves you. Yeah, the algorithm doesn't need to become active. However, if that is not provided, the algorithm provides also a performance increase, but only by a factor of 200 roughly, 200%. Yeah? You see here, the algorithm is basically a compromise. The number of retransmissions without the algorithm is somewhat like what happens basically. When you lose the packet, you're halving the congestion window, and then there's maybe a RTO, retransmission timeout, then the congestion window is 1, and you're evolving until you reach the next segment. This is basically what is shown here. If there is a packet loss, you lose bandwidth, and then you have to go for a couple of retransmission timeouts until you sending again an in-order segment, and then you peak again. Yeah? So this is basically what's happening with the number of retransmissions here. You retransmit every segment in the retransmission window in the current transmission window, and then you are again in a steady state operation. This is how you break the loss chain without the algorithm. If our algorithm, however, is in place, it breaks the loss chain immediately by performing a bulk or a go-back-end retransmission. This bulk retransmission, however, could be in vain if you have another packet loss in the sending window, but so to say in the retransmission window. So you lose a bulk retransmission, once again a segment, and what you end up with is a bulk retransmission storm. So you are pretty fast, but you're sacrificing lots of bandwidth. You get a lot of throughput, but not that much goodput. Yeah? So how could you fix that? And this is something we didn't do, because we then said, okay, let's stop there, maybe the wrong direction. We come back to that later. What you would need to do is basically also change not only which segments need to be retransmitted, but how the segments are retransmitted, and then our retransmission control algorithm would be a real congestion control algorithm, right? This is where we stopped, because summary, we had a lot of insights and a lot of learnings there. And these are the learnings. Our retransmission algorithm is augmenting the TCP congestion control. It's not a congestion control because it's just changing which segments are retransmitted, not how and when. It's not affecting congestion window, all that stuff. It just says how to do which segments are due for retransmission. It is detecting whether the remote TCP is supporting out-of-order queuing or not, and reacting adaptively on that. So it's adjusting its operation scheme to help recovering or healing the system. Yeah? It can increase efficiency, but it tends to lead to bulk retransmission storms. What we also have seen, it can never outperform a TCP implementation that does support out-of-order queuing. And that is basically where I now want to give you my my meter summary of prospects. Engineers sometimes tend to optimize things that should not exist. Here, we optimized, or actually came up with a workaround for a problem that should be solved. That's the very same thing. We should solve the problem in the first place before coming up with a workaround. Yeah? So my message is use TCP. Max, if you want to use TCP with out-of-order support whenever possible. And again, don't use too much TCP. Thank you.
Okay, so we're taking the questions now. Okay, on the right, maybe. Yeah.
Might be a question for clarification because I've not fully understood the entire picture. So TCP comes along with a flow control and a congestion control. And there, I would say in the meanwhile, perhaps 20 of these controls.
Thousands.
At least discussed in the IETF. And the IETF is the technology owner of TCP, and that we're still having a maintenance working group in order to coordinate all the TCP activities. And of course, there are many system and operational contexts TCP is used, and this in-vehicle network, I think it's limited to the in-vehicle network only, is a managed internet, so this is an intranet, and then of course you could configure these controls as you like if you use, let's say, standard congestion control or flow control algorithms. Yeah. So is this just a specific TCP protocol profile specification, or is this extending an existing control?
It would be, you could add that to any existing control algorithm because that's a retransmission, so it's on top. That was the idea. Let's, agnostic of the underlying congestion control, let's add something. Yeah. It's an engineered network. We should therefore try rather to prevent packet losses and maybe not rely on TCP too much unless you have really proper TCP implementation, and the proper one are typically off-board communication. So there is a head unit, an antenna ECU that is doing internet streaming via TCP. That's okay for me. There is an embedded stack trying to do TCP with so limited resources. That's a problem that I tried to tackle, but eventually I was pushing hard in getting the out-of-order queuing supported, the reordering feature, so that this is not needed so much. Yeah. So it's rather an academical solution and a learning journey, a learning experience, what I shared with you.
Yeah, this would be the second question. So this is a single TCP connection segment. If you go outside the vehicle, this is a typical case, then a TCP connection is crossing multiple network borders. And then you have TCP to TCP in the working modes, and then again, various different TCP to TCP gateway types. So
could be the case, yeah.
And then it might be that the controls algorithms are just changing.
Yeah, this was pure in-vehicle, addressing an in-vehicle problem of embedded stacks. Yeah, I don't want to chase the other stuff. It's okay. It's complicated enough.
And for the automotive SDN folks, there's a young module, of course, for TCP protocol endpoints as well, in order to configure such controls.
Okay.
Thanks, Karl. Absolutely agree with the conclusion. Question is, if we do need reliable communication between two ECUs, where we want to make sure the order of packets is preserved and all packets get there and it's not last is best, do we need a different solution, and what keeps us from using something like a stop-and-go protocol, like I think it's TFTP or something like that, where we say, I send a frame, I tell you go ahead, I send you a frame, go ahead. I think the whole bandwidth of the go-ahead is not a problem. I've heard in the past that potentially the scheduling of the sending task on the transmitter might be a problem because that limits the line rate. Is it useful in investigating such a thing further?
I have two answers. So one of the problems that we currently face is you created that one. Because actually the UDS should have never be on TCP. Yeah, it has its own retrial.
It wasn't meant to be used between ECUs. That was introduced later.
I agree. But it escalated, right?
Yes.
So that answer means also that there are only limited use cases for TCP. So maybe the problem is not that big currently. However, the second aspect I would like to share on that, I'm always driving or motivating application developers to don't do application development fully agnostic of the network. And if you don't do that, there are lots of applications that all of a sudden don't need TCP anymore because you did something more clever in the application. Yeah? And then again, a part of the problem disappears. So this is maybe not the solution that you want to hear, but this is currently our pragmatic approach, so to say.
I'll take that as a clear and definite maybe.
Yeah.
Okay, so one last question.
I wanted to ask something that kind of follows up on what Max said, which is I look at this and I look at the ECU that doesn't have out-of-order support, and I say, well, why does it advertise a window size? That seems to be sort of counter to what the TCP protocol wants you to do, right? So
yes, very good question.
Have you characterized the bandwidth where the ECU that doesn't have out-of-order support just advertises a window size of one packet, 1,500 bytes?
Then you don't have the problem. You have an excellent observation. That is something I think I did not mention. These retransmission storms, they're subject to the size of the window and the failure rate, the packet loss rate, right? And if you just shrink the problem, but then you have just a ping pong TCP, right? You're wasting a little bit of bandwidth there, but you avoid that problem with the lost out of order queuing. I'm not sure why this solution, I think the implementers wanted to look as if they did TCP, but they were not committed to really do TCP. Yeah? Maybe that is the solution why we see that stuff.
I asked specifically because I had a vendor that was doing this to me. It was not interoperating with our Linux host very well, and I basically slapped them and said, you're advertising a window size and you have no queue. Cut your window size to 1, deal with it. Yeah. And we're only using it for firmware updates, and I don't care. Zoox doesn't care how long the firmware update process takes. It takes an extra 10% or whatever.
I've seen that as a solution in serious production, achieving decent throughput.
And yeah,
what you're
the
suggesting.
solution was fine, right?
Yeah,
nobody complained that it was any bit slower. So we've seen that as
I've seen that working.
As a standards compliant solution and something that works with the embedded ECUs as they are.
Yeah, standard compliant. The problem is, me as an OEM, I need to write a system specification. Yeah, and now I need to distinguish between dumb systems and powerful systems. You could do that, but then your colleagues are asking, am I a dumb system? Not sure how to answer them.
Well,
no, you're
not.
not.
My answer there is very simple, right? You tell me what your queue size actually is. Yeah. If you're not able to queue packets, don't tell me you can queue packets.
Yeah, that is the most important answer. Don't tell me you can queue packets if you can't, and then you can. But again, writing specifications gets then all of a sudden almost like writing code and a lot of if then else. You can go with that, or you just say, okay, let's solve the real problem again. Your solution is the same what I did, right? I tried to solve the problem with a clever algorithm implemented on the powerful ECUs, and now you say, just live with it, just look away. I would argue, no, fix it. It's not that cost intense. Really, it's really not that cost intense. And we did that now. Yeah, our ECUs are all supporting reordering. Another reason why this one is.
Yeah, right.
Yeah, back to wherever you push it under the table.
Thank you.
You're welcome.
Thank you, Karl. Now we can move to the closing remarks by IEEE and Amber.